Today I'll talk about laminar flow through a circular pipe. After that I will derive velocity profile and shear stress distribution inside the circular pipe. Now here is the statement. So consider a laminar flow through a horizontal round pipe or circular pipe as shown in the figure below. The flow proceeds in a cylindrical coordinate. For equilibrium of a cylinder radius r contained in a lamina of radius r plus dr, then the net pressure force on the cylindrical element due to the pressure P and P plus del P on its end must be equal to the shear force on its periphery due to the presence of cylindrical element. Now consider, so this is you can see that this is that circular pipe. Okay, so you just take that cross sectional view. Now we take that small ring element that has thickness dr, okay, and length is dx. If you consider the dx length of that cylindrical element, in that surface the tau is acting, and as flow is coming from that left to right, so here that pressure force is acting, and opposite side the P plus del P, that pressure is acting. Now at equilibrium, if we consider that here the flow is fully developed flow. Now if I balance the force, so force will be here. So the net pressure force on the cylindrical element due to the pressure and P plus del P on its end must be equal to the shear force on its periphery due to the presence of cylindrical element. Now if we do that force balance on a cylindrical element, so here this side will be that P pi r square, and opposite side means minus that pressure is acting the negative direction, that P plus del P pi r square. So that is equal to that tau is the shear stress acting on the surface into that area, so 2 pi r into dx. So now if we simplify, we'll get del P pi r square, so P pi r square and pi r square will be cancel out, so minus del P pi r square is equal to tau 2 pi r that del x. Now tau will be half, so del P by del x r, because here this is the partial, but as it is varying in one direction, okay, only x direction, so it will be ordinary differential equation. So tau will be minus half dp dx r. So hence the shear stress is actually tau is equal to minus dp by dx r by 2. Okay, so this is the shear stress on that cylindrical element. Means if you vary r, we can easily get what will be the shear stress distribution. Now here, if the laminar flow in a pipe is fully developed, the velocity profile does not change in the Now talk about shear stress and velocity profile. Now if the laminar flow in a pipe is fully developed, that is the velocity profile does not change in the longitudinal direction, the velocity u varies only r, and the pressure P remain constant over the cross section. Under such condition, the longitudinal pressure gradient will be dp by dx remain constant. So hence tau is proportional to r, that is shear stress varies linearly with radius. So maximum shear stress occurs the pipe wall at r is equal to capital R. So tau max will be minus dp by dx r by 2. So here we got tau is equal to minus dp by dx r by 2. Now if we put r is equal to 0, that means here that the center, so what will be tau? Tau will be 0. Now if r is equal to capital R, so tau will be tau max. So now if you write that y is equal to that mx plus c, so c is actually 0. So now that line, so there will be no intercept, so that tau actually varies linearly. Okay, so at the center it is 0, and all tau will be maximum. Okay, so that is the distribution shear stress profile. Now coming to the velocity profile, so we know that tau is equal to that mu du by dy. Okay, now so if we, here we have to as it is a circular pipe, so we have to change that y to r. So now here from center to that cylinder surface, the distance are actually r. Okay, and here from that surface, whatever element we are taking, so from that surface to that wall surface, that is y. So now we can write that y is equal to nothing but capital R minus r. Now dy is nothing but minus dr. So tau will be minus mu du by dr. So that is very important. Okay, now we got the relation, right? Now we know that that tau is equal to minus mu du by dr. Now and that minus du by dr is nothing but minus, because this is tau, so tau is minus dp by dx r by 2, and dp by dx is constant. So now from here, so du by dr is nothing but dp dx r by 2 mu. Now if we integrate, so u of r is equal to dp by dx r square 4 mu plus c1. Now c1 is the integration constant. So now we have to find out the integration constant. So for that we need to apply boundary condition. So what will be the boundary condition? We know that at wall no ceiling boundary condition, because there will be no that velocity at the wall. So we have to use that boundary condition. So u is equal to 0 at r is equal to capital R. Now if I put that boundary condition in this equation, so we will get that 0 is equal to dp dx r square by 4 mu plus c1. So c1 will be minus dp dx r square 4 mu. Now from here, so now if we plug that c1 in that equation, so we will get that u of r is equal to dp dx r square minus small r square by 4 mu. So this is the velocity profile we got. Okay, now here, so if r is equal to 0, what will happen? So u will be u max. So u max will be so dp by dx then capital R square by 4 mu. So that is the u max, and r is equal to capital R. What will be the u? U will be 0. That is at that wall. Okay, so means this equation is correct because that it is satisfied the boundary condition. Now we got u max also. Okay, now here ur is equal to dp by dx r square minus capital R square minus r square by 4 mu. So if you see here, so this is nothing but a parabolic profile. Okay, so now velocity will be that parabolic profile. So this shows that velocity profile is parabolic with the maximum velocity at the center. So here you can see that the center will be the maximum. So this is a parabola. Okay, and u varies with different r. Okay, and r is 0 at the wall. So velocity profile inside the circular pipe is parabolic profile, and profile is like that. So next we got ur is equal to this. Now if we differentiate, so du by dr will be so dp by dx r by 2 mu. Already we got that. Okay, so now here shear stress is nothing but tau y is equal to mu du by dy, or mu is equal to minus du by dr. So from here we will get minus mu dp by dx r by 2 mu. So minus 2 dp dx r by 2. We already got that. Okay, and then tau yx is equal to that minus dp by dx r by 2. Now at r is equal to 0, r is equal to 0, so tau y is equal to 0. So here you can see that r is equal to 0, tau is 0, and at r is equal to capital R, that tau will be tau max. So that will minus dp by dx r by 2. So shear stress is maximum at the wall of the pipe. Now what will be the total discharge through the pipe? So total discharge q is nothing but integration of dq. So that is 0 to what? 2 pi r u dr. So we know u. So we plug, and then if we do the integration, ultimately we will get that q is equal to that pi by 2 mu dp dx r square by 4. Okay, so that we got that the discharge. Okay, now here okay, q is equal to ultimately, okay, so here there will be some minus sign. Okay, so minus sign will be here also there will be minus sign there. So pi by 4, okay, 8 mu, that dp by dx, that will be the q. Now this is the total discharge through pipe. Now average velocity, that q by pi r square. So if we do that, so we'll get that u will be that minus 1 by 8 mu dp dx by r square. So now here dp by dx will take care of the negative sign, okay, because minus dp by dx actually is a positive, okay, because that when that flow is flowing through this direction, so upside that the pressure will be higher and that pressure will be low at the downside. So dp dx actually the negative, so that will take care, and u will be minus 1 by 8 mu dp dx r square. So that will be the average velocity. I think that's it. Thank you.